Welcome to my channel, A Brain in a Vat. I received a letter recently. Dear Brain in a Vat, what exactly is pi? Why does it matter? What does it mean that it's irrational? And if I have memorized more than 20 digits, does that automatically qualify me as a nerd? On that last question, unfortunately, no, it only qualifies you as a geek. To be a nerd, you actually have to memorize at least 100 digits of pi. So what is pi exactly? Well, first of all, it is a mispronunciation of the Greek letter P, just like in our alphabet, LMNOP. There's also the Greek letter P, which is mispronounced as pi. So pi is simply the ratio of the circumference of a circle to its diameter. Now, why does that matter? It turns out it matters a lot in geometry, calculus, physics, all kinds of stuff in the real world. But what I'm going to try to do right now is explain where the number came from and what makes it irrational and why does it matter. So the circumference of the circle is just the length as you go around this, and the diameter is just the length through the center. So if you take this ratio, that is what pi is supposed to be. Well, how do you actually figure out what that number is? Well, here's what we do. We start, let's say, with a square. And what I'm going to do is I'm just going to call this length right here to the center, I'm just going to call that an R. Eventually it's going to mean radius, but I'll just call it R for the time being. So the circumference then, which is the this plus this plus this plus this, if this length is R, then obviously this length right here is going to be 2R, which means that the circumference is nothing more than this plus this plus this plus this, which is equal to 8R. And then the diameter is just going to be 2 of these, so 2R, which means that the ratio of C over D is just going to be 8R divided by 2R is equal to 4. You might say that that is the most, the roughest, the dirtiest possible approximation of pi. Probably offensive to a lot of physicists, but this is the simplest, maybe you would say the first term in deriving what pi actually is. So now what I want to do to get a better approximation for the actual value of pi is I'm going to break this up into a few pieces. So we're going to keep this original value as R. And now, whatever length that is right there, I'm going to keep that length. What I'm going to do is I'm going to go around this whole thing and just cut off little equilateral, well, they're not equilateral, little right triangles off of all the edges. The idea being that this length is R, and this length is R, and this length is R, all these lengths are R. Notice what I've done here is I've modified the square to remove this portion, and this portion, and this portion, and this portion, all 8 of these portions, and I'm going to add on this portion, and this portion, and this portion, and this portion. So we can do that actually pretty simply using some geometry. I want to keep this really simple and straightforward. What I want you to note, because this is a right angle, what I want you to note is simply that this length right here is necessarily less than the sum of these two lengths right here. That's all. That's all I want you to notice. So in other words, what we're doing is we're taking the original circumference of the square, and we're subtracting off this and this, but adding this, and we're doing that 4 times. Because this total length is greater than this length, and we can show that using the Pythagorean theorem, but I think you can just see it, right? I mean, this plus this is pretty obviously, optically, larger than this length. Because of that, what that means is that now when we take the circumference of the octagon, which is now the blue portion, when we take that circumference, which is to say adding up this, 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 and this, that number is going to be less than the sum all the way around here. It must be, because this portion is less than that portion right there. Right? The shortest distance between 2 points is a straight line. So if you're going from here to here, the shortest distance is going to be from there to there directly, not taking this detour like that. So what that means is that the circumference of the octagon, I'll call that 8 for 8-sided, is less than the circumference of the square, which is the 4-sided version. But the diameter, which is from here to here, is still 2r. So the diameter remains exactly the same as it was before. So what we're doing in order to find the ratio of the circumference of the octagon to its diameter is we're taking the circumference of the square, subtracting off, I'll use a different color, subtracting off 4 of these, and then adding 4 of these. And what that means is just that the circumference is going to be less, and so therefore the ratio of the circumference of an octagon to its diameter is going to be less than the circumference of the square to its diameter, and this number, of course, we know was 4. So all we're doing is we're just subtracting off a bigger piece and adding on a smaller piece, okay? Now, is an octagon a circle? Well, no, but it's certainly a better approximation for a circle than a square was, right? An octagon looks more like a circle than a square does. If you were going to make a wheel, a really crappy wheel, it'd be way better to make it out of an octagon than a square. So let's now start with the octagon and try to get an even better version of a circle. And of course, the way we can do it, so we've got kind of a stop sign here. Now, if I want to make this look more and more like a circle, then here's what I do. So the radius, again, was this, which is also the same as this, which is the same as this, and so forth. But now what I'm going to do is so this portion right here, I'm going to slice off another triangle. So I'm going to slice off a little piece of a triangle here, and a little piece right here, and a little piece right here, and a little piece right here, and so forth. And if I were able to draw this properly, then these would all be the same triangles all the way around. And so notice then in that case, this also has a radius of r, and then to here has a radius of r, and so forth. All these pieces have radii of r. But now let's blow this up. Let's look at this triangle right there. You know, it looks something like this. And notice again that this length plus this length is necessarily greater than this length, simply because the shortest distance between these 2 points is going to be the straight line between them. If you have to take a detour, that's going to add length. Now we can use the properties of geometry and the Pythagorean theorem to actually show what those values are. And you would need to do that if you want to calculate what pi actually is. But I'm not trying to do this. I'm just trying to simply show that this length is necessarily less than this plus this. But you haven't gone nearly as far out of the way in this example as we did before when we were going from the square to the octagon, where we had, you know, we're going much further out of the way here and going from the square to the octagon as we are from going to the octagon to the sixteenagon. So because we're going less far out of our way in this example, even though it's true that this total length is greater than this total length, it's not that much greater than this total length. It's not as great a difference as going way out of the way here. So what this means is that in going from the eightagon, the octagon, to the sixteenagon, we are subtracting this length and adding this length. But now that difference between the two is even smaller. So in other words, we can, so we're going to do this now, 8 times. So now we've got a situation where the circumference of the sixteenagon is definitely less than the circumference of the octagon, which is less than the circumference of the square. But when you go from here to here, that's a bigger loss than when you go from here to here, because you're not losing quite as much in going from here to here, because in each case, you're not going nearly as far out of the way. So now let's imagine where we keep dividing that polygon into, now it's a 32agon, now it's a 64agon, now it's a 128agon. Well, when you get to the point of being a regular 128agon, which is to say it has 128 equal sides. I mean, there's no way I could possibly draw this, right? But what happens is it starts to look very much like an actual circle. Like you probably could comfortably ride on a wheel that was actually a polygon with 128 regular sides. Probably be better to, it'd be better to be a circle, but the point is this is a reasonably good approximation of a circle. But now, in going from the 128, here's the R, the 128agon to the 256agon, now you're going to have to kind of zoom in to this portion right here, and what you're going to see is that it is a really, maybe this is where this would be helpful. It is a really, really minor, practically inconsequential distance. And I've drawn this so I can't even use my paint stirring stick to go all the way across, but I'll give it a try here. So this is the example where now this line represents the one side of the 128agon. This segment right here represents one side of the 256agon. And again, it is a shorter path to go straight between these 2 points. But if you didn't go straight, if you actually just went out of your way to this point to make it the 256agon, you're not going very much out of the way. It's a really, really, really tiny portion. So again, using basic geometry, you can just calculate how small that value is. I'm not going to, but it's tiny. And the point is that by the time you get to the circumference of the 128agon, and now you want to go to the circumference of the 256agon, yes, it's less. It's less because in doing so, in going from here to here, what you have to do is you have to subtract off this portion right here and add this portion right here. But they're so close to each other that they are almost the same. So if you want to derive pi, so basically if pi is the ratio of the circumference of a circle to its diameter, what you're going to do is you're going to start with the circumference of the square, and you're going to subtract off a little piece. I don't know what that's going to be. And then you're going to subtract, corresponding to changing this to the octagon, you're going to subtract off another piece that corresponds to going to the 16agon. You're going to subtract another piece that corresponds to going to the 32agon, and so forth. You're going to basically just keep subtracting little pieces off infinitely many times, and then divide it all by d. And then that is what is going to give you the value of pi. Now you can truncate this after a certain point and get a really good approximation for pi, and that's exactly how, that's one way that it has actually been done in the past. But something I want to point out is that really a circle is the same thing as an infinity-agon, right? Because the idea, that's a terrible infinity. The idea is simply that it has infinitely many sides. So instead of having 256 sides, you keep doubling or increasing the number of sides to make a regular polygon until eventually the length of any individual side goes to 0. And so when you sum that all up, then you get the circumference of a circle, and then again you divide that by d, and that gives you pi. Now, there's a couple interesting things to note. The first is that pi does not exist in the real physical universe. It doesn't exist. And the reason it doesn't exist is because it is the result of an infinite sum. You have to keep subtracting off portions until you get to the value of a circle, and you have to do that infinitely. Well, you can't do that in the real world. The physical world doesn't have infinity. Infinity does not exist in the real world. Okay, so let's say you want to actually measure pi in the real world. What you do is you start with a circle, and you actually just take out a tape measure, and you measure its circumference, and you measure its diameter, and then you just divide them, and you'll get a number. Of course, there's going to be errors, experimental errors, and so generally the larger the circle, the better your value of pi is going to be. Well, the problem is the universe is only so big. So even if you could measure the circumference of the universe, which you can't for a lot of reasons that I won't go into, even if you could measure that, and even if you could measure the diameter of the universe, keep in mind that there is, because of physics, because of quantum mechanics, there is a limit to how precise you can make any measurement. So imagine, for example, if you just were able to measure the circumference of the universe down to the Planck length. I'll write it. In another video, I'll explain why that's more or less a useless value or number. But at the very least, physicists agree that you can't physically measure anything shorter than the Planck length, which is on the order of something like 10 to the minus 34 meters, in that order of magnitude. So if you can't measure anything better than a resolution of this, even with the entire universe, even if you could precisely measure that value down to the Planck length, which you can't, but even if you could, and even if you could measure its diameter down to the level of the Planck length, which you can't, but even if you could, you're still going to get a value of pi that's, 50 or 80 or 100 digits long, and that's it. So, does pi exist with infinitely many figures in the real world? No, absolutely not. In the physical world, absolutely not. Now you can calculate pi to as many digits as you like using this procedure or one of many other procedures, and computers do that. But they don't have any real world significance or meaning. And part of the reason is that because you have to go to infinitely many sides to calculate pi, and because infinity does not exist in the physical world, then you can't actually calculate pi, and pi is what's called an irrational number. Now, an irrational number, you probably remember from maybe junior high or high school, is a number that does not terminate or repeat. So, for example, 1/9 is, and it continues like this, but it repeats. It repeats a 1. So that means that this is a rational number. A rational number is simply a number that can be expressed as a fraction a over b, where a and b are integers. That's all a rational number is. And so the question is, why is pi irrational? Well, the answer is because it cannot be expressed as a fraction of a over b. But how do we know that there is such a thing as an irrational number at all? And the quintessential example is the square root of 2. The square root of 2 basically means what number, when squared, gives you 2. Well, the square root of 4, there's a number, 2, also negative 2, when squared, give you 4. So clearly the square root of 4 is a rational number. But what about square root of 2? Well, square root of 2 is not rational because there is no number, say a over b, which when squared gives you 2. Now I'm going to prove this very quickly right now just to show you. You can do something like this. So this is a squared over b squared equals 2. Multiply both sides by b squared. That gives you a squared is equal to 2b squared. Remember, a and b are integers. I haven't said anything else about them. I've just said that they're integers. So if a squared is equal to 2b squared, and b, remember, they're both integers, this must mean that a squared, this arrow that I draw means implies, that must mean that a squared is even. It has to be, because if you square an odd number, you get an odd number. But we already know that 2 times anything is an even number, so therefore this side is even, therefore a squared must be even. But if a squared is even, the only thing that squares to make an even number is an even number, because an odd number squared gives you an odd number. So that now implies that a is even. Okay? Now, when you square an even number, you'll get a number that is a multiple of 4. So what that means is that, what this implies then is that a squared, even if you divide it by 2, is still even. If you think of any number, let's start with 6 as an even number. 6 squared is 36, divided by 2 is 18. That's an even number. So a squared over 2 must be even. But a squared over 2 I just rearranged these, is b squared. So if a squared over 2 is even, then that implies then that b squared is even, and that implies that b is even. Okay, no problem so far. We've just shown that if this is true, if a and b are integers, such that a divided by b squared equals 2, then a and b must both be even. So we say, all right, we screwed up. They have a common factor in them of 2 at least, and there may be some other factors. So let's do this. Let's go ahead and cancel out all the 2's in the top and bottom. Just cancel them out until they're all gone, which means you cancel them out until either A or B or both of them is odd. That's it, right? You can do that. So like the number, 14 over 4, for example, those are both even, but you can divide the top and bottom by 2, and then that gives you a 7 over 2. Well, that's now a fraction that you can't reduce any further. So this is an odd number, this is an even number. So that's what I'm going to do. I'm going to go back to this and specify that not only are these integers, but they are not both even. That is to say, there is not a factor of 2 in both of them, because if there were, I can always reduce that factor of 2 out until I get an equivalent fraction that I can put in here. Now, I hope you see the problem. The problem is this proof was insensitive to whether or not A and B were both even. I simply started with this value and concluded that A and B must be even. But now I go back and say, well, let me change my mind. Let me specify that at least one of these is odd by just reducing the fraction. And I run through the exact same proof and prove that both A and B are even. And that is a contradiction. And when you have a contradiction, what that means is that at least one of your assumptions is false. And so that means we assumed that there was some integer A and integer B, which are not both even, such that this is true. We got to a contradiction. Therefore, we were wrong. There is no ratio of integers A and B, which, when squared, gives you a value of 2. Now, having said this, does that mean that the square root of 2 is a real number? Well, it's a real number by definition. They call those real numbers. Is it real in the physical world? The answer is no. Square root of 2 does not exist anywhere in the physical world. And the reason is the physical world is made up of stuff and fields and particles and waves. And all of those have values and dimensions that have limits on their measurability. They are not infinitely precise, and therefore you cannot have something with a decimal that goes on infinitely without repeating in the real world, because there's not enough information in the universe to actually specify that. So when I claim that the square root of 2 doesn't really exist, and I'm saying that as a physicist, not as a mathematician, and it doesn't really exist, what I mean to say is simply that there is no rational number which, when squared, gives you the value of 2. Just as the square root of 2 does not exist in the physical world, neither does pi. Neither one is a rational number. Neither one exists in the physical world. But they're both very, very interesting and useful in a mathematical sense, and also in calculating things about the real world. Now, in calculating, we still have to truncate each of these numbers at a certain point, depending on the accuracy or the precision that we need. But we'll never need a pi with greater than 100 digits. We'll never need a square root of 2 with greater than 100 digits, because you can't get that kind of precision out of the physical world anyway. I hope that answered your questions. If you have other questions on topics of physics or mathematics or consciousness or free will, or any question on the philosophy of physics or science, feel free to visit my blog, which is inavat.com, for brain in a vat. And you can email me directly at aknight@alum.mit.edu. Thanks for your time.